Hello, this is Nick of Time. Welcome to this, our 18th talk in our series on the physics of time. This talk is the start of part 3, where we take what we learned in part 1 and 2, and we begin to build a new physics of time. Thank you so much for joining us today. Unfortunately, when I had an update on Windows 10, that knocked out my video camera. So we'll just be a disembodied voice today. But that makes a good point about critical thinking. It's not who is talking, whether they have fantastic credentials or don't have fantastic credentials. You got to focus on the content. So the first thing we learned in our part 1 and 2 was it's time to change how we treat time in physics. Specifically, we reject the basic construct of special relativity's treatment of time. We reject the following. We reject defining time in terms of the speed of light. Second, we reject single clock's rate as being observer dependent. If we use that model, then if we compare clock A's rate to clock B's rate, we come to the qualitatively glaring contradictions, because the theory says that clock A's rate is faster than clock B's rate, and clock A's rate is slower than clock B's rate. Not good. We reject clock rate as a function of relative velocity, and the focus is on the word relative. Clock rate is the function of absolute velocity, but it's not a function of relative velocity, which would again lead to contradictions. We reject special relativity's construct of relative simultaneity, because that gets rid of one of the primary properties of time, namely the past, present, future construct. And kind of as an aside, we reject time morphing into space. Time is fundamentally different than space. I don't have a QED argument for that, but for example, one of the properties of time is that there's an arrow of time. You only move forward in time. You don't move backward in time. That property is not in space. If I'm on the x-axis, I can not only move to the right, I can move to the left. And when time morphs into space, I don't know how they explain losing the arrow of time, and if you go back from space to time, how that property gets re-injected into time. And there are a number of examples like that. Somewhat of an aside, we'll take a quick look at general relativity in time. General relativity's field equations for gravity are fine as far as time is concerned. And in fact, we discussed how general relativity's so-called time dilation as a function of gravitational potential is fine. There's no logical contradiction there. It's a reasonable candidate as a description of what happens physically. And in fact, the empirical evidence seems to support it. That doesn't mean that general relativity is necessarily correct, because other theories can hold that clock rate is a function of gravitational potential. General relativity's problems come from grafting special relativity's errors onto general relativity. But general relativity's curvature of space-time may be okay for math modeling, but not really a very good physics model, especially for time. Okay, we've rejected relativity's treatment of time, but that doesn't mean we're going back to Newtonian concept of time. We're avoiding, but not necessarily rejecting, Newton's philosophical construct of absolute time, which advances at the same rate for the whole universe. It's kind of a nice, natural, intuitive construct, but it's philosophical and very vague as to what the physical meaning of that is. So we're going from the philosophical construct of time, and we're replacing it with proper time. That's how we're going to base our physics of time, use proper time, which is an excellent physics construct since it's operationally defined. For a particular clock, its proper time between event 1 and event 2 is the amount of time that accumulates on that clock. And all observers have to agree with that or they're wrong, because that's how it's defined. It's the amount of time that accumulates on that clock between event 1 and event 2. And event 1 and event 2 have to be on that clock's world line. In other words, the clock has to be at event 1 and event 2 to talk about its proper time between event 1 and event 2 for that clock. As a side point, if we look at the twin paradox in this construct, whenever relativists have alleged a reconciliation argument between the claim that special relativity describes a net proper time difference in the twin paradox scenario, if we restrict ourselves to looking at what that argument says in terms of proper time, we immediately see the flaw in that alleged reconciliation argument. So sticking to proper time is a great tool for really seeing the true physics of time for different scenarios. So, to get to our new physics of time, we do the following. We use proper time. We use fundamental physical processes as the basis for the time in physics, such as the atomic clocks and the fundamental vibration rates of atoms. Further, we define universal time. That's kind of like absolute time, but it's fundamentally different. We define universal time in terms of our knowing the physics of proper time for different absolute velocities and for differences in gravitational potential, which will change from location to location. So clocks will go at different rates. Identical clocks will go at different rates depending upon their absolute velocity or depending upon their location and the gravitational potential in that location. But because we know the physics of those different rates and the effects of those physical properties, we can create a universal time. We can say that, okay, we know that clock A accumulates proper time twice as fast as clock B. So then we can relate those two proper time rates and coordinate them. So 10 seconds for clock A may be the equivalent of 5 seconds for clock B. Different number of seconds, but we can make sure the same proper time rate can be derived for both. Okay, we reject relative simultaneity, and we define absolute simultaneity using the above, using proper time, and making sure we know how the proper time rate of one clock relates to the proper time rate of another clock. And basically, that's using the GPS model of establishing absolute simultaneity and universal time in the vicinity of the Earth. So it's not just some wild theoretical thinking. It's very practical thinking, and we have a good model, working model for it. Okay, let's do a summary of our new approach to the physics of time. We're going to base it on proper time, which is operationally defined, user independent, which makes it absolute and unambiguous, and therefore those properties help it to be an inherently good physics construct. We get rid of relative simultaneity, replace it with absolute simultaneity and universal time, which restores the construct of past, present, and future in physics, and that construct is a fundamental property of time, and it's great to have that fundamental property of time restored to physics. So next time, we will continue on this new theme about building a new physics of time, and hope that you will join us then. So thanks very much for joining us this time. Hope to see you next time.